Yeah, so today we have Mahimna coming from Cornell Tech, and he'll be talking about his exciting work to appear at CCS this year on complete knowledge preventing encumbrance of cryptographic secrets. So take it away.
Thank you for inviting me. I'm happy to present our work. This is joint work with Vishal, Phil, James, and Ari from Cornell Tech, and Vitalik from the Ethereum Foundation. So the central claim of this paper is that cryptography models a simple form of knowledge. And this leads to a bunch of attacks which I'll classify under the umbrella of encumbrance attacks. And this paper will be a way to fix the problems that are caused. So what do I mean by saying cryptography models a simple form of knowledge? Let's take some simple examples. So for instance, intuitively, we say that Alice knows a secret as K if she can furnish it as private input to the protocol. So let's say we have a protocol pi, which does a bunch of steps. Suppose in step I, it tells Alice, okay, compute y equals some function f of your secret key and input, and send this to Bob. So in our traditional mindset, we can think about this as Alice owning the secret key as k, the input x, computing it locally, and then sending it over to Bob. So what this paper considers is a setting in which this secret key as k, instead of being held by Alice, is actually held inside a trusted. And this turns out to be a problem, as we'll explain. So effectively, the scenario is as follows. Instead of the secret key being held by Alice, it's held inside trusted hardware, which provides Alice the functionality when Alice inputs x, the trusted hardware provides f of fk x, and then Alice forwards that to Bob. And the idea here is that most of the protocols are indistinguishable to whether the key is actually held by Alice or the key is held in trusted hardware. So a remote party can't actually distinguish in most cases whether the key is held in trusted hardware or not. And this turns out to be a problem, as I'll claim in this paper, and we'll call these sort of encumbrance based attacks. And I'll show, yeah.
Can't you ask the trusted, like if you ask like the enclave to like sign the
so
whatever you
in the honest case, there is no enclave, right? So it's actually held by the user. So if you ask the enclave to sign it, there is no enclave. Right?
I see.
The enclave is sort of an attack.
I see.
Okay. Yeah.
Okay, I'm interested why that's an attack.
Okay. So maybe let me.
If you always get the enclave to sign, like enclave will always have like an additional. Whenever it outputs a secret, it'll output the secret with the signature. But you can just remove the signature.
Remove the signature, yeah. It also doesn't always output this. You can run whatever programming. Maybe let me like get into the model. So just to provide some background on trusted hardware, you can think about it as like a hardware black box running at some computer that has some program running in it that's specified by the user and some data that's to be on. And the trusted hardware provides two properties, integrity and confidentiality. Integrity means that the operating system or other processes can't tamper with the control flow of this program. And confidentiality means that the operating system or other process can't learn anything about what's going on in this program. Another property that's typically found in these trusted hardware boxes is property of remote attestation, which essentially means providing a proof to a remote verifier that a particular program is running in the trusted hardware. So the trusted hardware here, Intel SPX, can provide an attestation that can be verified by a remote verifier, which requires trust in the platform here, so Intel in this case, that a particular program is running inside the hardware, and this is the correct output from running that program. So that's sort of the background of the trusted hardware model. And now I'll talk about the problem, which I'll call encumbrance or key encumbrance when we're talking about secret keys. And the problem is as follows. So in a very small nutshell, the idea is instead of exposing any functionality of the secret key, you expose just a partial computational functionality of the secret key. And this is as follows. So think about the secret key here, instead of being held by Alice, it's now held by trusted hardware. And the program running inside the trusted hardware essentially takes in an input and produces an output corresponding to some functionality of the key in the input. But the program only responds to approved inputs that are injected by some other party or hard-coded. So this essentially means that the program is giving only a partial computational functionality to Alice, instead of in the case where Alice held the full secret key and was able to compute anything with it. And the idea is like encumbrance is also possible through MPC. So you can think about another potential encumbrance pattern here, where Alice and Carol have secret shares of the key. And they run an MPC protocol, but with an additional parameter where Carol can approve which inputs is Alice allowed to access the MPC. So essentially, the output of the MPC protocol is f of input comma the key, where the key is again secret shared between Alice and Carol, but the output is produced only if the approval function is true on the input. So this is a way where Carol can selectively choose what outputs Alice can get. And so this is the kind of thing that you can do in MPC, but just for a simpler sort of intuition, we'll think about this encumbrance as being done by trusted party. But again, like this kind of encumbrance can also be done by MPC. And kind of the central starting point is it's actually not very easy to identify. Let's take two cases here. So on the left, we have Alice with full access to her secret key. And because she has full access to it, she can sign any message. On the right, you have the secret key inside a trusted hardware box that allows signing all but one message. So it will sign any message that Alice requests as long as the message is not the string. And the idea is like these two worlds actually turn out to be vastly different from a protocol perspective. And we really need to differentiate between the two. And I'll provide sort of these attacks on encumbrance-based attacks. But first, yeah.
I'm trying to figure out whether encumbrance is like good or bad. Are you trying to say we only want Alice to be able to run particular inputs in this thing, or are you saying we want Alice to be able to do anything, but the trusted hardware might not?
So okay, so basically what I'm saying is the encumbrance is used as an attack. So basically the idea is we cannot distinguish whether the key is fully held by Alice or held inside trusted hardware. And because of that, in the case where it's held by trusted hardware, this leads to a new class of attacks called encumbrance attacks. So it's actually required that we be able to distinguish
Class of attacks from
attacks, I'm sorry.
like you said, class of attacks. So give your attacking.
Yeah, so I'll describe attacks in the next few slides. So we want to distinguish between this is like the high level idea, but like just to give you a picture of why this is not that trivial, you can think about, okay, why don't we use like a proof of knowledge protocol that Alice owns the secret key? It turns out that the proof of knowledge protocol doesn't work because the same protocol can be executed inside a trusted protocol. So for instance, this is a very simple proof of knowledge protocol where the verifier sends a random challenge message and the prover submits a signature on that message. So this is the normal case where Alice owns the secret key. But in the case where the secret key is actually in the trusted hardware can also simply respond to the proof of knowledge protocol. And as I talked about before, let's say the secret key inside the trusted hardware doesn't respond to signatures for the message hello, it responds to everything else. This proof of knowledge protocol still works because you don't know what message won't be signed by this hardware. In a sense, encumbrance allows proving knowledge without actually having it. So you can kind of see here that if the trusted hardware has the secret key instead of Alice, nobody really knows it. But the proof of knowledge protocol still works, which means you're sort of allowing proving knowledge to the verifier without actually having it. This is sort of the crux of the problem. And and our paper introduces what we'll call proofs of complete knowledge to fix this gap between what we think about knowledge and what proofs of knowledge actually.
Okay, I mean, I guess like in my opinion, like I guess maybe this is just like saying like the problem differently, but it's like the same model. Like what I would say is that actually like you are getting a proof of knowledge, you just don't know who you're interacting with. Like so it's actually like just a problem that like your channel is like I mean like of course always when you ask Alice like hey can you prove this to me if this is true, like if Alice has friends, like these friends can like answer Alice's question. And like Alice and her friends know the secret.
Yeah, so I mean, so the point is here, nobody has like here in this case, arguably nobody has knowledge, right? Because it's just the trusted
party. Like joint Alice like T entity, like
sure.
Knowledge. Maybe this is just like
yeah, so okay, in that sense, you can also think about this as like a proof of individual knowledge. So you want to prove like knowledge is for a single party instead of NPC having knowledge, like having knowledge where keys are secret shared or like trusted hardware plus knowledge. Okay, knowledge. But I'll talk about like why this is actually relevant, and I'll describe some encumbrance attacks. So the first one is quite simple but powerful. And the idea is you can break deniability in end-to-end messaging without detection. So for some background, deniable messaging protocols like Signal work as follows. So essentially, you have two communicating devices here, let's say Alice and Bob, taking part in this end-to-end protocol. And Alice is sending a message to Bob. Bob reads the message. And the idea about deniability is that Bob can't convince a judge that Alice said whatever the message. And this is because essentially Bob also has the ability to forge any transcript that can be sent in this deniable messaging protocol, so the judge won't believe that Bob did it for him. But the idea here is if the key that Bob has for this end-to-end messaging protocol, instead of being owned by Bob, is actually held inside this trusted box, then this gives Bob the ability to tell the judge, hey, look, I'm locked inside a trusted hardware box without the ability to forge. So the program running inside the trusted hardware does not allow me to use the key to forge the transcript. And it can use this as convincing proof to the judge to break deniability on Alice's message. So essentially, Bob can prove to the judge what Alice said without Alice actually knowing that this was.
So I'm a little confused by this because like Bob gets to like see like whatever it wants to see. So like it can just say something like, here's a message like from Alice, like, or something. I mean, as long as it can like, I don't know, like as long as
there's authentication, right? So all this end-to-end messaging protocol will have authentication. So Bob can authenticate that it's coming from Alice.
Okay.
Right. But Bob can't prove to the judge.
I see. So they like share some individual keys between them.
Yeah. So there's
yeah, okay. All right.
So it's both, yeah. So for the authentication part, there will be sort of a public key card thing. And for like the deniability part, use it. Does the deniability thing make sense? The second kind of cool thing I'll talk about is a trustless collusion and bribery attack. So here's sort of the scenario.
Actually, sorry, it doesn't make sense. So, like, what thing was Bob able to do between like what? I still don't understand. Like, I guess there's like.
So before, Bob couldn't prove to the judge that Alice said whatever.
Right, because this protocol has.
Because Bob has the ability to forge the same transcript.
Yeah.
So the judge wouldn't believe him.
Right.
But in the new mod, like in this encumbered kind of setting, because Bob's key is inside trusted hardware with like a program that say doesn't allow him to forge, he can show the judge that, hey, look, I'm inside a trusted hardware box that doesn't allow me to forge, so I couldn't have forged this message, so it has to have come from Alice. So you're sort of breaking deniability for Alice's messages without actually Alice knowing.
So for like basic like deniability, like
messaging protocols will support deniability? Like, is it necessary for Bob to have some key for the deniability to work, or like I don't see why like this breaks deniability. Not sure. So what is the property? So what is the property of the deniability protocol that having this trusted hardware bypass? So the Bob's ability to forge the message. So typically deniability is achieved by Bob's ability to forge the message. So you can also think about it in terms of like designated verifier proof, right? So if you give a designated verifier proof, it's essentially saying either this statement is true or I know the secret key, right? And like you use this using the verifiers. And now the verifier knows that they didn't like give their secret key to anyone else, so that's why they know the statement, right? But if they like send it to someone else, then the other person's not going to believe them because they could have forged this transcript using their secret. But like in a similar fashion, think about that key being in trusted hardware and now showing to the remote verifier, like remote judge, that I can't forge. I don't actually know. Right. So this is like in a similar way that you can break deniability, you can also break designated verifiers because they rely on the same sort of function. Okay. The second thing I'll talk about is a trustless collusion and bribery attack using Encumbrance. So here's sort of the setting. So at a high level, think about a voting key for a user being held inside trusted hardware in a sense that it allows all possible other irrelevant transactions to go through. So any irrelevant things with respect to this one particular election are allowed to go through. But for this one particular election, it will only allow messages to be signed voting for a candidate. So the idea here is that Alice and a briber can collude trustlessly to encumber the secret key that's corresponding to the election inside a trusted hardware. And the idea is Alice doesn't care about this election, but she cares about using her key for other purposes. This is a special case in which the voting key is also used for other activities, which is pretty common in like a blockchain setting, where you want to potentially access your wallet, which is controlled by the same key that's used to derive, let's say, your vote. So by encumbering your wallet key itself, but allowing the trusted hardware box to sign messages that correspond to just sending money. But for this one specific election, only allowing voting to sign for voting messages that are voting for blue. This allows sort of Alice and the briber to trustlessly collude in the following way. So Alice doesn't care about the election. She can do whatever she wants to do. She doesn't own the key, but to her perspective, she can do whatever she wants to. And the idea is the briber is now guaranteed that Alice in this election will only vote for this particular candidate. Like provably, she can't vote for anything else because the trusted hardware owns the key and won't allow Alice to vote. And the cool part about this, I won't go into too much detail, is there's a long line of work on coercion-resistant protocols, which actually doesn't solve this attack because this attack actually breaks the assumptions involved in this work. So typically, there's assumptions made about an untappable channel that the voter can use to register with like the voting service, or the idea that they actually own their keys so they can generate fake keys to give the adversary. But in all these cases, require the voter to actually have full access to their key. So by breaking implicit assumptions in these coercion-resistant protocols, you can have trustless coercion that essentially gets around this line of work.
I'm still confused. Like, what kind of attack is this? So who designed that program? That only is it the?
Yeah, I'm also
So basically Alice and the briber are colluding. The program is specified by the briber as like, okay, only vote for this particular candidate, blue. Don't vote for anyone else. So the trusted hardware only allows voting for a particular candidate decided by the bribe. Alice doesn't care about this election, so she's willing to be bribed, but she wants access to her key for everything.
Like, how does it work? Like, how does the briber even get to like fit in Alice's key into a program. Like isn't Alice given her key and she's like, yeah, my key's in this program and I'll only do it with this program. When she submits to the protocol,
So
she can sign with like the key that she knows, her key.
So let's take as a very, very simple example, think about the registration phase of the voting protocol.
Okay.
So instead of doing it as like as normal, you basically do the registration phase in a way that the key gets put into a trusted hardware box whose program is like controlled by you.
Like, yeah. Sure, you go. I don't know what would happen.
No, this is because Alice actually wants to close. So this is like a way for Alice to get paid for selling her phone.
First goes through
Yeah.
Alice.
No, it doesn't go through Alice. It directly goes in this.
Okay.
I think all this comes down to like the program in the TEE isn't what someone thinks the program in the TEE is. Like in the deniability example, it's like, you know, Bob, I assume, thinks that, you know, his messaging app gave him like the normal protocol that's using the normal secret key, but then it turns out he got this like messed up protocol that will do everything normally except for the deniability like functionality. And like somebody, my understanding of the issue is that we think the program is doing the honest like voting protocol, but actually the program is a slightly modified program, and I'm also not quite clear on like who actually decides what the program is. And in this case, I get that like yes, it could have been that like the computer owner or something could have been trying to do that. But is it right that the like crux of the issue is what's the program in TE?
So in the normal model, there's OTE, right? So from the remote person's perspective, so let's say I'm a remote party and they're running some protocol with you, right? And in the normal case, you own your key, right? In the attack case, your key is actually in a hardware box. That gives you only a partial functionality, and I can't actually distinguish which one of these is true. So in one case, you have your honest vote, but in the other case, your vote can be sort of bought, or you can collude with a briber to vote only for a particular. And that's kind of the main crux of this.
In this case, it's like Alice and Briber, they all know that programs.
That's right.
And the rest of the world.
Exactly. So here, Alice and the briber are on the same team. They're actually colluding but they don't like sort of trust each other, right? So if Alice can take the briber's money and run away with it, but like vote for whoever she wants, then that's not viable for the briber to pay.
So one thing Alice can do is just not vote.
I don't think.
Yeah, so I mean, you can design the program in a way that you won't.
Okay, like maybe.
Yeah.
But I guess also you could do something really insidious, like if this briber was doing this with 1,000 people or something, they could say like, do the normal program 99% of the time, and then like, 1% of the time change red votes into blue votes or something.
Yeah, like you could do a lot of like very interesting and powerful attacks. So this, like, you could basically have the briber kind of buying votes from many users by encumbering like all of their keys. You can actually also create a marketplace for buying and selling votes for any of these like online voting protocols, where on one side you have voters who want to sell their voting power, right? On the other side, you have bribers who want to pay to buy this voting power, and you actually don't even need them to know each other. You can create this sort of dark marketplace, which we call it dark DAO, to sort of have this buying and selling.
He generated first. I mean, someone has to generate.
So for an intuitive level, you can think about, like, let's say for the voting purpose, what the voting key that's generated, instead of it being generated, like the protocol being done by the user, it's sort of being done by the trusted hardware. So the trusted hardware is the only one that will know the key at birth. So you sort of, yeah.
Sorry. Oh, I mean, the only thing I was gonna say is that like But doesn't the protocol like already require like however we generate the keys require like fact like oh these like people that want to sell their votes already have the public keys, secret keys, and it's going to like I don't know encrypt however like say it's generated under a PC that's going to encrypt under their public key whatever their voting key is.
So think about the wall. No, so think about the wallet itself, like whatever the original public key private key itself being generated by the person. So you sort of generate the key itself, like generate Alice's key at the start in trusted hardware, right? You transfer all the assets into this new key. So now everything that you own is actually held by an encumbered key. And then you take part in this like voting protocol. So I'm like,
here that Alice is just going to like this enables a collusion between these parties that was previously difficult because Alice can like literally like deposit her identity into this SGX and such a way that she'll know that her identity is only going to be like manipulated in ways that she hasn't agreed to beforehand.
Yeah, exactly.
Okay.
So basically this requires like Alice to approve putting her own key at it. So by the way, I'll say like a lot of these attacks were actually noticed by prior works. What we do is sort of combine them under the umbrella of this encumbrance framework. Okay. And then we provide it.
So is it crucial that Alice knows that the program has been manipulated?
Yeah, Alice is on the same side.
So what if like I pretend to be a legit like whatever program seller? I tell them here's whatever. Like this is the SGX generated wallet, and here's something I changed. And because you don't actually vote, you don't.
I mean, you need to rely on Alice like actually being able to run with the program, or like run the program and make sure, or like see the program code and make sure it's in line with what she thinks it's doing. Right.
But in practice.
That's a difference.
Would that so in the messaging deniability? I guess my impression was that Bob didn't know that he like he just downloaded the modified signal app or something. The keys were in hardware the whole time, and he maybe didn't even know he couldn't.
You could that could be one possible setting, but you could also have a setting where Bob actually changed things about the app, and he uses this basically to show to a judge. He wants to break exactly. Yeah. So that's like the more concerning setting because you can break deniability for someone else. So yeah, we actually have a follow paper on dark DAOs, and we built a prototype dark DAO marketplace for this sort of interaction between buying and selling.
Seems like there could be constructive uses to dark DAOs, right? Like
Yeah,
here
essentially, yeah.
there should be.
Yes, there are. Stay tuned for some work. Yeah, not in this talk, but yes. So, okay, so sort of the crux of all of these attacks is encumbering the key. So the idea is, can we detect when the key is encumbered, and in a sense, establish individual ownership of it. So what we essentially want is what I'll call complete knowledge. So before I get there, let me provide some intuition on why standard proofs of knowledge don't work. So you sort of expect proofs of knowledge proven that's been studied for several decades, provides would be the perfect fix for this, but I provided some context of why it doesn't work, but I'll provide more detail now. So just for some background, what are proofs of knowledge? You can think about this as like an interactive or non-interactive protocol between a prover and a verifier, where here we have Alice, who's the prover, who wants to prove to Bob, who's the verifier, that she knows some secret. So for intuition purposes, you can think about a secret key corresponding to a particular public key. But more generally, you can think about this as proving for some public statement X, you want to prove knowledge of some witness W, such that f of x comma w equals 1. So most commonly, this relation is an NP relation. So you want to prove knowledge of a witness corresponding to the statement X being in that NP. So a couple properties that are required for proofs of knowledge. The first is completeness, which simply says that an honest prover, so this is a prover that has access to the witness W, can always convince the verifier. The second is soundness, which means that a cheating prover, this is one that does not have access to the witness. So this cheating prover cannot convince the verifier. And typically for proofs of knowledge, you have a knowledge soundness property that actually assumes the standard soundness from interactive proof systems, which is as follows. So if the verifier was convinced, then there is an efficient extractor machine that can interact with the prover and recover the witness from it. And just as a footnote, proofs of knowledge don't need to be here. Yeah, so we do need like sort of non-rewinding proofs, but essentially that's not sort of enough. We want it to be sort of practically instantiable. So in a sense that I'll talk about this in the next slide. Actually, so the idea is the extractor is very often a theoretical proof construct. So it's typically used to make proofs go through. It doesn't matter if it's sort of practically instantiable or not. So for example, in a lot of cases, the extractor gets access to the code or sometimes Oracle access to the prover. And this actually may not always be practically well-defined. So for instance, if coming back to our original model, where if the secret key or if the witness was held inside a trusted hardware, what does it actually mean for the extractor to run on the trusted hardware and extract the witness? So if we assume a hardware assumption that the trusted hardware is secure, then nothing should be able to extract from the trusted hardware box. Right. So essentially, there's some mismatch between the extractor, which is often theoretical, getting access to the prover and being able to extract from it, and sort of being able to extract in a practically instantiable.
Yeah, I mean, okay, I'll keep listening. I'm a little confused about this mismatch. I mean, it just seems to me like, you could imagine running the code of the trusted execution environment again, like, I don't know. Yeah, I'd have to see like how you write down what a trusted execution environment is, like theoretically, to be like, oh yeah, it's not something you can extract from.
So I'm just saying, like, for intuition purposes, let's say we have a hardware-based assumption that you can't extract. It's a hardware assumption.
Like, what does it mean you can't extract? The way we're not
like it's a black box that has some secret in it that you can't like get out of it. Like, no matter.
But I think the idea here is that like it's not the way you get it out is not by like looking in the box, right? You get it to like send you messages, right? And you could like run it.
But you can't rewind it. Like in a lot of these. Anyways, maybe like this would be clear. Yeah.
You have to have either like some kind of CRS or some kind of hiding problem, but otherwise
Yeah.
verify that we do it.
So
Like somehow the extraction has to be more powerful than the verifier.
I'll actually get to the model. I think it's somewhat interesting. So maybe we can talk about like more.
I feel like extractor has always been a theoretical concept. Like, what does it mean to rewind in the real world?
Sure.
You can't rewind the real world.
Yeah.
So
in a sense, like you can also think about this being like one way you can have the extractor be concretely instantiable. So my high-level claim is for a proof of complete knowledge, the extractor is concretely, practically instantiable. And I'll talk more about that when I describe the formals, and then maybe we'll so just kind of reiterating some stuff. Like at least we want it to be straight line, which is like, it shouldn't rewind the prover, and we want it to be non-programming, so it shouldn't be able to program the other. But I'll talk more about what I mean it to be practically Okay, so I'll describe what the formalism for proofs of complete knowledge looks like. So what's the setting for this? So the first thing I'll say is you do need some sort of hardware-based or resource-based formalism in to define proofs of complete knowledge. And the reason for this, you can think about NPCs being complete. Whatever you can do as a single party, you can also do with an NPC. So you shouldn't, like, if you didn't have any sort of other assumptions, so in like a standard model, you shouldn't be able to distinguish whether a key remotely was held by one party or held in NPC. And similarly, anything that you can do with a single key owned by an actual party, you can also do with that key owned by trusted hardware. So we have this new formalism that uses that has like a hardware assumption baked into this resource formalism. And one of the assumptions, for example, I'll use is a timing-based one, as some hardware will compute faster, and I'll talk about that in our program. But let me talk about the setting here. So instead of having the extractor as a theoretical proof construct, what I'm going to do is actually physically instantiate an entity, which I'll call the eavesdropper, which will sort of function as the extractor. And here the picture is as follows. So you have your prover interacting with the verifier in this proof of complete knowledge protocol. And the prover is connected to a resource that is the thing that will actually enable doing the proof of complete knowledge part. And there's a channel from the prover to the resource, which this entity E, called the eavesdropper or the extractor, lies in. And the idea being that the interaction channel between the prover and the resource will be seen by this entity E, and using just that information, it will be able to recover the secret of proof of complete knowledge. So here, essentially, instead of, again, the extractor being kind of a theoretical construct, it will literally be the channel between the prover and the resource. And basically, the extractor will be able to extract the witness just by observing. So this is one way to sort of model a practically instantiable extractor, and it's the way we do for our work, and we show how. Just communication. There's
just like share secret.
Yeah, so I'll get to, so this is where like the resource assumptions sort of come in. So the idea being is you can only do the proof of complete knowledge with a specific set of resources. If you use something else in a way that this extractor cannot extract, then you won't be able to. That's kind of high level. So this is where the hardware assumptions. And I'll get to this in the next couple of slides. Okay. So in terms of formalism, there's a standard part of the formalism, which you can just typically think about as copying like standard proof of knowledge formalism. There's a setup phase, which can generate like all the public parameters, and the prover and verifier can be thought of as an interactive proof system, where the prover is given these public parameters, the statement X, the witness W, the verifier is given the public parameters. We have a new addition to this formalism, which is like the resource based ones that I was talking about. So I'll define two sets here. So I'll define first the set R of approved resources. So intuitively, these are the resources that honest provers would use to prove complete knowledge to the verifier. And these are the resources that would allow extraction by E. And there's a second set, which is a larger set, R pract, which is a set of all practical resources. So essentially, this is where we'll encode hardware assumptions for our protocol. So essentially, the adversary still needs to use resources in this practical set. And the idea here being is that if the adversary uses any resource in the practical set, either you wouldn't be able to convince the verifier, or if you do, the extractor. That's kind of the high level picture. Let me kind of specify that more in the properties. The first one, again, is completeness, which essentially changes just the resource part. So instead of an honest verifier being able to convince honest prover being able to convince honest verifier, now we say that the prover is able to convince the verifier using an approved resource. So as I said before, approved resources are the ones that will allow this eavesdropping or extraction to extract out. The second property is soundness, or what I'll call forced revelation. And the idea here is, as I was saying, no adversarial prover can convince the honest verifier using any of these instantiable or practical resources. So even an unapproved resource, as long as it's practical, without the extractor being able to. So if the adversarial prover uses one of these unapproved resources, then either the verifier is not convinced, or if it's convinced, then the extractor. And this again, this rpract allows us to encode hardware assumptions about resources into the protocol. So there can be some resources outside of this set rpract which allow an adversarial prover to prove complete knowledge to the verifier. But by assumption, these resources are not. And that's kind of the high level. And the third thing I'll say is the zero knowledge property can be defined very similarly as
Can you maybe go back to the bribery example and like explain how this formalism works within that example?
Maybe I'll describe the protocol.
Oh, yeah.
So basically, all this is to prove complete knowledge of the key. So it's not held inside trusted hardware, it's held inside, or it's basically held by the user, right? And the secret protocols will allow you to do that based on the two different. Yeah.
Okay, actually, at the beginning you said you can kind of do this with MPC, like that you can think of the trusted hardware as like a second party. And we're now gonna, it's gonna refuse to answer. Is that just sort of encapsulated in the resource?
Yeah.
Now?
So essentially, like you also want to prevent that, right? So as I was saying, like you can have the extractor working on the MPC protocol in the standard modeling, but not on individual parties. And we'll use a hardware-based assumption. So in particular, for that one, we'll say that MPC will be slower than purpose-built hardware, which is like unencrypted. So I'll use these ASICs for the hash. So I'll talk about two protocols for CK. The first one is actually an STX protocol, kind of a fight fire with fire kind of situation, where the resource is an STX, so essentially a physical instantiation of a trusted third party. And the way or the reason why you can extract from this resource is the communication channel to this particular honest STX will be unencrypted, and so it can be. And I'll talk more about this in the protocol. The second protocol is one that uses a proof of work mining ASIC. So essentially sort of a physical instantiation of a random oracle. So essentially we embed a Sigma protocol into a proof of work transcript. And the idea for extraction here is that the communication channel to the ASIC is unencrypted and that can be eavesdropped. And at the same time, the ASIC computes significantly faster than any machine using like an encrypted channel. So for example, using like multiparty computation like a trusted hardware CPU, the ASIC will be significantly faster. So we'll use a computational resource assumption for this one. Yeah, so very good question. So if that works, then this protocol would work. This is kind of embedded into the hardware. So if there is an ASIC that is encrypted and can compute as fast as like a normal ASIC, then this protocol would.
Yeah, then I just like go and why would people use your hardware? Like if I want to do this, why would I?
So currently there is no encrypted ASIC that computes hash functions as fast as normally.
Oh. Okay.
So this is basically the idea is like this is all embedded into a hardware assumption.
Okay.
Right? So the assumption, I'll get to the protocol, but the assumption is that this ASIC, which is unencrypted, will compute hashes much faster than any sort of trusted point. including potentially an encrypted, which doesn't exist. And even in a world where it exists, you can imagine the unencrypted one still running faster, as long as there's a computation gap between the two, you can parameterize.
Yeah, but like these gaps are kind of hard, but well, maybe no, maybe. But this the first assumption, so you're just like assuming that they're running on an honest SGX that like runs a certain protocol for you.
So not assuming that they're running on SGX, but that is like the approved resource. So if you use like a bad resource, then you wouldn't be able to.
And the prover now, if you strap this, like you extract the resource out, then the prover is just a machine, like access to the oracle. The oracle is the only thing that cannot be rewinded. So if you allow the extractor to access to the prover,
so I think it potentially can be done that way, but I think the crux of this was we want sort of physically instantiable extractor, which means in most cases in practice, like you can't actually rewind like the sheet.
Right? Why would you want to physically?
So okay, maybe let me actually do it this way. There's actually a subtle challenge here. I don't think I have a slide for that, but the subtle challenge here is actually you need the resource to actually, like, you must use the resource to prove complete knowledge. And this is actually implied by our soundness property. So even if you just had access to the prover and you did rewinding, it wouldn't actually deal with this. You actually, without the prover using the resource, you will not be able to convince the verifier. This is all very weird formalism. I completely agree with this because it's a non-standard way of thinking about knowledge, but it is the only way that actually shows a particular, like basically individual knowledge of a secret rather than. Okay, I'll talk about the first protocol, which is this trusted hardware-based complete knowledge. And the idea is, you want something similar like 5-fire. So, okay, you have a prover talking to a verifier, and the prover has this honest resource SGX, and the honest program that's running is very, very simple. So the program is as follows. The prover just submits the witness to the SGX in an unencrypted channel, so the SGX just accepts the witness in plain text, checks the correctness of the witness, and signs it, and outputs this. And this plain text channel between the prover and the resource is essentially what will allow eavesdropping by the extractor. So anyone with access to this channel, including the prover, will be able to use that to retrieve. And now the prover can just send the signature to the verifier. You can verify two things. The first one is this remote attestation from the SGX that proves that the SGX is running this honest program. And then you can just sort of verify the signature using the master public key of the SGX. And the hardware assumption here that we actually need is that SGX cannot be simulated inside another SGX. And I'll mention this in the next slide. But you can kind of see that first, completeness is easy to hold because an honest verifier, honest prover, can just submit the witness to the SGX and get a signature out of it that verifies. And soundness holds because for two reasons. The first is this SGX signature can't be forged by any other resource by assumption. And the second one is the extractor, which sits on the channel between the prover and the resource, will be able to extract out the witness because it's sent in plain text to this honest resource. So I mentioned that the assumption you require is that SGX cannot be simulated inside another SGX. And what does this mean? So what you could end up having is an inner trusted hardware and an outer trusted hardware, where essentially this outer hardware functions as an encryption and decryption box to this inner honest SPX. So if you could sort of place this honest SPX or approved resource inside of an outer trusted hardware that just does encryption decryption for this inner SPX, then you wouldn't be able to make this protocol true because now this outer SPX would know the witness, but nobody outside of it. Does that sort of make sense?
Does this stop the MPC encumbrance kind?
Yeah.
Like, what is the assumption here when it comes to MPC?
So the assumption here is like this SPX is one physical like machine, or it's on one physical machine. So even if it's an MPC, some party in that MPC protocol will will need to provide witness to its SPX. There's some machine or some party in this MPC which has full knowledge of it. So it's not actually held inside MPC. Like one individual party will have access.
One more question. This seems like not ideal because the witness is sent in plain text, and that is
To
usually
your sort of local channel.
okay. So your SPX is like the voting system has to send an SPX to every voter.
Or not send it, but like this, basically to make this proof, you need an SPX on your.
But
It's not that the voting platform sends it, but it
Okay.
it accepts the proof from this SPX program. So this proof requires honest users to own it.
but also a malicious user can claim that they have some SPX, and how could
So a malicious user, so in this case, is like one that doesn't have the witness, right? So the only way you can provide a proof from this honest SPX is by giving it the key, giving it the witness, right? So there's this, any actual physical machine that has that SPX will be able to recover the witness.
Like what if an SGX allows me to do like a lot of things? Like it might not like output the witness for you, but like it'll output like signature that it has.
No, so the remote party is verifying that you're running this particular program on the SPX, which just takes the witness and outputs the signature. So this remote party is verifying that you're running this honest program.
Yeah, but why wouldn't running my honest program on this SGX?
Can you repeat?
I maybe see. I mean, I'm just thinking like, okay, maybe I have my SGX, and like my SGX just has this. Like, I don't have the witness. I have an SGX. My SGX can like run this program, and it will attest for running this program. It will attest for knowing the witness. So
how will it attest for knowing the witness? You need to provide the witness to the SPX.
To the other SGX.
To the SPX running this program. You need to provide the witness to an SPX running this exact program. So there's two things that are checked, right? So one is that SPX is running this exact program, and the signature. And the signature is only given when you provide the witness.
So I have an SGX. Like I'm an attacker.
Yeah.
I have an encumbered secret. I have an SGX.
Yeah.
It's holding the witness for me. And then I tell the SGX, okay, like that, can you run this program? And then can you output a signature for me? Like that you ran this program and that you have the witness and whatever. And then I just send this out. Like I only have one SGX. So it's like
So you need to provide the witness on like unencrypted to the SGX. So the thing that you're working becomes problematic if you have like an SGX inside another SGX. So this is your honest SGX. Okay. And think about there's like an outer SGX that like you send an encryption of the witness to, it decrypts it and sends it to the honest SPX in order to get a signature. Right. So that's kind of the only way you can deploy this.
Okay, yeah, sort of.
Okay, the second protocol is this ASIC. How much time do I have?
maybe 5 more minutes somewhere?
Okay. The second protocol is this ASIC-based complete knowledge, and the core idea is to embed a Sigma protocol into a proof of work mining transcript. And okay, so the hardware assumption here is that the intuitive reason why this protocol works is that the ASIC will be significantly faster in computing than any form of encumbrance using hardware or MPC. And I'll talk about that. So I'll just very briefly summarize Sigma protocol. So the Sigma protocol is like a 3-round proof of knowledge of a witness. So the 3 phases are as follows. In the first step, prover submits the commitment A. The verifier then responds with a challenge C, and the prover submits a response S. So the transcript is essentially this 3-step protocol, a 3-step protocol with ACS. And typically these protocols have this special soundness property, which means that you can extract the witness from 2 transcripts with the same commitment and different challenges. So if you have 2 transcripts of the form ACS and A C prime S prime, then you can extract out the witness. So how do we use this in our proof of complete knowledge protocol? So the idea, again, the diagram is as follows. You have a prover and a verifier running this Sigma protocol, and you have the prover that's connected to the honest ASIC resource. And the idea, so the high-level intuition is you use a proof of work mining on the Sigma protocol transcript. You take the Sigma protocol transcript ACS, you hash it with some nonce, and try to find a nonce such that the hash is smaller than some. And that will sort of be your proof given the square. That's a very high-level picture. And the reason for that is this channel is eavesdroppable by the this extractor, and we'll use special soundness on this channel to extract. So essentially, we'll have the prover, even the honest one, submit 2 transcripts for the Sigma protocol to the resource, and this will allow for extraction by the extractor E. And only one of those transcripts will be submitted to the verifier, the one that finally completes. Yeah, so maybe let me talk a bit more in detail. So the Sigma protocol proceeds as normal. You have a commitment to the prover. So instead of the verifier sending a challenge C, it'll send some randomness R, and you'll use this randomness R to compute multiple challenges. And basically the idea is you take some nonce mu, compute the first challenge using a hash of R and mu, and use that to compute the full transcript ACS. And now you'll try the proof of work mining to see if there's a nonce that satisfies the hash being bought. And the high-level intuition is that the range of this challenge and like the nonces will be chosen such that with high probability, the prover will need to submit multiple challenges, at least 2, in order to get like a valid proof of work solution. And the fact that it submits at least 2 of these challenges to the resource will allow for extraction. And finally, you can just have the prover submit the Sigma protocol transcript along with these 2 nonces, one for the challenge and one. And now for validity, the verifier will just need to check that this proof was submitted in a specific amount of time. The idea being that the honest prover who has access to unencrypted ASIC resource will be able to compute this proof within the amount of time, but an adversarial prover who can only use sort of encumbered channels like trusted hardware and MPC won't be able to complete the proof. And you can sort of run this for many steps in order to reduce stuff. I will skip this. So we have prototype implementations of both of our protocols. So for the first one, we implement for the ASIC one, we implemented on Ethereum as follows. So we have the verifier actually is a smart contract in Ethereum. We parameterized it to work with the 12-second block time on Ethereum. And it turns out that we can actually use ASIC hardware that's several years old, so something like $100 currently. And the protocol provides soundness and with just 12 rounds. And if we use a state-of-the-art ASIC instead, it's significantly faster, so this only requires 8 rounds. So essentially, yeah. So here, so you this entire protocol is going around, and you can run it many, many times. The second one is the TE-based protocol, where instead of using an SGX, which maybe not everyone has, we have sort of a lightweight CK implementation, which uses Android devices. So TE is found on Android devices, which can be more accessible. I'll talk about two cool applications that are made possible only by CK before wrapping up. The first one is I'll call key coupling. And so the idea here is proving that two keys or addresses belong to the same entity. And it's essentially you want to prove ownership of X and Y. And you can kind of see that standard proofs of knowledge don't work, because I could know one key, you could know the other, and we could compute an MPC that we own both of them together. But neither of us actually knows both. And this kind of proving both of these keys are owned by the same party is useful for things like tax accounting. So if I'm sending money from my own address to another of my own addresses, then I can prove that I own both addresses, so I'm not, say, taxed on it. The second thing is what I'll call atomic assets. So assets that you want to be single owner or non-fractionalizable. So for example, blockchain representations of real world assets like houses or concert tickets, where you only want sort of one owner. So for a concert ticket, you don't want it to be held by like many people. You want like one physical owner. And that's something that can be achieved by complete knowledge, because you can't sort of hide it under MPC. So short takeaways here are, this work shows that encumbrance creates problems for cryptographic protocols by essentially violating assumptions about key ownership that are implicitly made. We provide a solution called proofs of complete knowledge, which enables proving individual ownership of secret witnesses. And the high-level takeaway is, in a lot of cases, if your protocol doesn't use the proof of complete knowledge, it might be vulnerable to these new class of encumbrance spaces. I'll end with that. A link to the paper. Bye.